I'm Zac Sweers. I work at Uber, and today's talk actually has nothing to do with anything that I do at Uber. This is actually kind of an interesting talk because most of the talks at conferences like these and at this one, it's a lot of really good information, like things that you want to learn about, and then take back to work or to your side projects, and you want to try that yourself. It's like new architectures, new patterns, better ways of doing things, etc. With this talk is not like that. You should not do anything that I'm about to do in this talk. So if you take nothing else, take nothing, like literally nothing. So if you want to follow along the slides, you can find them at this link. There is a lot of code, so hopefully that'll help. And I'm just going to stall time for another like 10 seconds here. And not quite 10 seconds. But without further ado, let's talk about ClassLoaders. So first and foremost, ClassLoader is itself a class. It's been there since Java 1. It's a simple class with a sort of handful of grab bag of methods here. You got like load class, find class, define class, get resource. A lot of these, they do what they look like they do. And for the scope of this talk, we're going to be focusing specifically on this load class method. Now, class loaders are abstract classes that can have any number of different implementations. A conventional one that you often see is one called a URL class loader, which just loads from jars and directories. So the URL in this case is the URL to a container of classes. This is not actually what Android uses, though, and we'll get more into that later. Though amusingly, if you go digging around in AOSP code, you'll see that they at least thought about it. Hopefully that shows up there, but there's a to-do in here that says maybe we should try using URL class loader. So another thing to keep in mind is that they follow a delegation model. And what that means is that every class loader has a parent that they'll defer to. And in more recent versions of Android, the parent actually always gets first pick at this as well. It can be null, though, if you want to take complete control of class loading. And at the JVM level, there's a boot class loader at the root that has no parent. So in our previous example, that's this argument over here at the end. So what happens at runtime? So when a class loads, it comes through that load class method. So if we look at a simple example for this, say we've got this class foo, has a field for a bar type. When we load foo, it comes through here like this. And it's pretty straightforward. You get the fully qualified name, it loads it from the class loader, and then you carry on your way. You don't see this in your stack trace because that's not considered sort of like relevant to your code execution, but it is what's happening under the hood. And if you set a breakpoint in the class loader, you will see this fly through. Foo isn't the only class here, though. Bar is also a thing here, and we also need to load that. And the way that that ends up working is that it's loaded in the context of the foo above it. So when it comes through here, it says foo.class, get class loader, load class with bar. And it just continues this transitively for any other classes that come through any of the code that you're running. Note that this is done when code is hit and not necessarily everything up front. So a good example of this is if you have like lambdas or anonymous inner classes. If you have different classes that are loaded in their implementations, those aren't going to be hit until you actually hit that code at runtime. So what about in Android? So who in here is an Android developer? All right, let me try that. Who here is not an Android developer? All right, so 4 of you are going to be a bit confused on this part. But yeah, so as we saw earlier, Android doesn't use URL class loader. Instead, it uses something called a path class loader. Path class loader is a simple class loader that accepts a path to a directory of DEX files. And it's what's used at the system and application level for class loaders. It's actually one of a few different class loader implementations in the framework. So there's another one called a DEX class loader that seemingly, if you look at the source code, works exactly the same way. But the doc for it says it's explicitly for side loading. And both of these just extend a base DEX class loader. And this is where the main implementation for this lives. But it's also fairly simple itself, at least at a high level. Once you get down into how it works under the hood, then it gets pretty nitty-gritty and into framework code. Basically, it has this type called a DEX path list field, and this is really what does most of the heavy lifting. It in turn manages or delegates to a bunch of DEX file objects under the hood. And if you've ever worked with Android, you know about dex limits, dex files. This is where all of that really starts to actually make its way from the compiled APK into your actual runtime. Interestingly, in here, dex file is public, and you can totally access it, and it's part of the public API. Dex path list is not, so it's kind of like a weird case of like the thing that actually uses it can't be used, but the thing itself is public. But yeah, so that's sort of it for how it works in Android. But wait, you might wonder, the talk title is Breaking the Android Class Loader, and you're just telling me all the stuff that works. And we're going to get there. But first, I have to tell a quick story. So this is Utkarsh. Damn, come on. All right, let's try that again. So that's Utkarsh. He works on our scaling team at Uber, and he spends a lot of time on things like startup optimization, class loading, etc. And one Friday night, a few months back, I packed up my stuff, I was about to walk out of the office, and Utkarsh comes over to me and he says, "Hey, how's your reflection chops?" And I said, "They're okay." And he says, "Can you help me look at this thing real quick?" So I go to his computer, and for the life of me, I don't actually remember what specific code snippet he was trying to get working, but eventually I asked, what's the main thing you're trying to do here? And he said he was basically working on trying to improve startup performance by getting a better understanding and measurement of how class loading impacts it, and see if we can detect any sort of hotspots on that. But he was basically trying to create his own class loader that we would then go through and toss our DI graph up front into that, and then see if we could replicate the conditions that we were getting on startup. And so basically he's trying to create his own and replicate something by hand, and jokingly I said, well, why don't you just go and reflectively replace the one that's in the application, as a joke. And Utkarsh is one of the kinds of people that hears that and says, okay, let's try. And so at this point I had to put down my bag and sit down, and so we spent the next couple of hours trying to work on this and see how far we could get. We fully expected that it wasn't going to work, but then it did. So here's the story of that. First, we started with trying to see where ClassLoader is used, which that's 664 usages, so that's a lot. And we didn't want to go through 600 usages by hand and try to figure out which one was the right one. So we tried a different approach to actually see what ClassLoader was in place at runtime. So basically, you can in a context, you can access its ClassLoader, or in a thread, you can say thread.getCurrentThread, and there's APIs in there to see the current ClassLoader. So we tried that with the context, and then whenever we looked at it, it basically came up and said that we have a path ClassLoader, which is something that we had never seen before, and it's something from Dalvik, so it's clearly an Android-specific thing. And if you remember, that's actually the same one that we saw earlier as well. So we're on a good track here, so now we know what kind of type we want to work with. And after looking around at some usages in AOSP, it turns out all you need to do to create an instance of this is point it to your app's source directory. So this is where the app's APK file is on disk. And if you've ever worked with application info, like if you've queried intents or something, this is just that source dir field that is on that type. So we can create a path class loader with this. We can give it an optional parent. And if we want to instrument this, all we have to do is just create a base class of this, extend it, and we can then easily override that load class and start putting in our own logging in here, which is pretty trivial. So now we've got our working implementation, and now comes the hard part, or fun part, of trying to see if we can basically hijack the applications class loader with our own and see if we can start actually recording what's coming through here. So the quickest way that I can put this is we basically tried a ton of different places. This was, again, kind of going back and seeing where is ClassLoader used, and then trying to figure out how to get to all those points with reflection and set those fields. So first we tried the systems ClassLoader field, which is just a basic Java specific one. That didn't work, and or it didn't change anything that we could see. And seemingly on Android P and above, this actually will throw an exception at you. So next we tried setting the current thread, assuming it's the main thread's class loader. And again, we didn't see a crash, but we didn't see any logging coming through either. So by this point, we were kind of like scratching our heads and like, is this really the rabbit hole that we want to go down? And we got pretty close to giving up. And then we found this class called context impl, which, because remember, we knew that there was a class loader in context, and it seems like an oddly specific API to be exposing there if it didn't have some important value. So we go digging around, and we find this context impl class, which is hidden in the SDK, but you can go look at the source code. And this is actually sort of like, God context is unfortunately thrown around a lot in Android, but this actually is that. And it's the base context that all other contexts end up wrapping around, because this is the one that basically gets created at the core of your application and truly hosts all of your resources, assets, etc., and access to all of those things. So this is where the magic happens, and it has a mClassLoader field, which we tried that, but this time we got, it wasn't a case of running it and just nothing happening. This time we actually got an exception saying that the field wasn't found. And we're like, well, that's really strange. Like, this is an AOSP. I'm looking at the source code here, and it's not running on my Samsung right. So then we switched to a Pixel, and sure enough, it works. Or rather, the reflection works, but we still don't see any classes coming through our logging. So we're stuck with context impl again. Again, get pretty close to giving up. We tried a few other areas to kind of no avail. But there's another particular field of interest here, though, and that's a field called package info, which, interestingly, the type of that is called loaded APK, not package info. So we can go look in this package info field, and inside of the loaded APK type that it's that field is, there's a class loader field inside of it. And once we set this one, then boom, everything was coming through our right. Everything was coming through our logs. So it's a little bit blurry here, but you can see basically we're loading up some support library classes coming through here. We're logging. I don't know what the right unit is to use for measuring this kind of time. Like, I put in nanoseconds, but if you go to milliseconds, it just says 0 the whole time. So anyways, there's some unit that's best used to measure this. It's really, really fast and really small. Yeah, and that worked. So we've got a custom loader now. We've got a installation method for it to get it into our application class. And then it does a bunch of morally ambiguous reflection and runs on your phone. So naturally, we called it Black Mirror. Now for most of the rest of this presentation, I actually want to switch to sort of demo of different things that you can do with this information. And basically, it kind of pieces together everything that we learned from working on Black Mirror. And yeah, so if you want to follow along, all the source code for this demo can be found here. Just GitHub, Zac Sweers, Black Mirror. And this is also my second time doing a live demo and a talk, so expect disappointment. Yeah, so here we go. Bear with me as I get the... All right. There's that. All right, so this part's not going to be very readable unless I zoom in, and of course that doesn't work either. Okay, well, yeah, so at a high level glance, I know it's not very readable here, but we've got a very traditional Android project where you've got an app directory. We have a few different modules here. We have a subdirectory of different samples that we're going to go through. First one that I want to show here is, sorry, it's a presentation mode. First one I want to show in here is this Black Mirror class. So this is basically what I was talking about through the last segment that Ukars and I worked on a few months ago, which is basically how do we go through and have a mechanism to create a new path class loader pointing still to our APK, but replacing the one that is currently running our application so that we can basically record what's coming through and even intercept it. So there's a bunch of boilerplate going through here that I'm not going to get into, but this is that main installation method that comes through. You can see the main installation that we do into the context impl. We can also start running through, and you can see the different areas that we tried elsewhere. You can see some fun parts here where this will actually lint and say, hey, maybe you shouldn't be touching this. But fortunately, we can just suppress that, and that's fine. Sorry, any Android framework people here. Yeah, you can also see the part that doesn't work on Samsung, and yeah. It was great. After doing this, I then went through and added a static like is Samsung device method to our code base, which surprisingly didn't exist up to that point. Yeah, so that's the basic sort of installation setup. And you'll notice that I have these interceptors here. So if you've ever worked with, has anyone here worked with OKHTTP for networking? So most of the room, yeah. So OKHTTP has a nice, nice interceptor API, and we kind of basically wrote up something for this sample that does the same, where you can basically, it gets a request for a class, just the fully qualified name for the class, and then it returns a class result, which has the actual like class file in it. And you can basically read through it as a pass-through layer. You can short-circuit it if you want. So if you want to have caching or something, yeah. And without further ado, we can go into how this is actually wired in. So it's fairly straightforward. We basically just have a sample application. Whenever you So whenever you go through here, you can initialize it in onCreate, but you'll see here that we actually don't, and that's because you can actually go into a, there's a sneaky way to actually initialize things automatically before onCreate in your application, and that's through something called an init provider, or a content provider. So content providers get run automatically, and they're picked up from your manifest, and they get run before onCreate, but after the application is created. So we can't get quite as like narrow scoped as picking up all the class loading that runs in the application class during construction, but we can get everything starting in onCreate or later. And in here, basically, whenever your content provider is called, say Black Mirror install, given the context, and this installation method is pretty straightforward. And we can also give it a list of interceptors that we would want to use. So in this case, I've got a, there we go, a Black Mirror init provider. And here we actually have some interceptors. So the first one that I want to show is just a very basic one. This is basically what Utkarsh was trying to do that night, which is it comes through, it logs what the time, it logs what class is trying to come through, and that's it. And then we can see, what classes are trying to get picked up at potentially at startup or something, and we can see, hey, like maybe actually, this hot spot of classes coming through is unexpected here, or we've got something that could be done lazily. The next one that I want to show is a bit of a spin on that. So timing interceptor. So this is sort of a similar concept where we're logging something that's coming through, but this time we actually proceed with the full request to the class loader and then get the timestamp before and after. So we can actually see how long it took to load each time. And if we want to actually see this in action, hopefully everyone can see this okay. So we've got this sample app here. And we've got a few different options here. So when we run those timing and logging interceptors here, we can actually go through and dig them out of our logcat, and that's definitely not readable. But you should trust me that that totally says that it's timing stuff coming out of the class loader. And you'll see basically, yeah, it gets really noisy because there's a lot being loaded at runtime, especially if you have a particularly complex app or you've got a lot that goes on during your app startup or dependency graph initialization. But yeah, so it's very easy to just go into logcat and you can see all this coming through, and you can redirect or pipe that info however you want. I think Utkarsh actually did something where we piped the data on a test device to basically detect like where any particular slowdowns were. Yeah, so that's like a pretty like easy, trivial use case for it. And now I want to get into some more complicated ones or complex ones, and maybe ones that you shouldn't necessarily do. So one is a so if you've worked with the OKHTTP interceptors, you'll know that you can short circuit basically when you get a request coming in, which is to say, like, I actually know how to handle this response already. We don't need to go out and make the full, like, potentially like IO fetch for this. We can just return something immediately. We can also rewrite the request and potentially manipulate in a way to say we actually are going to request something else, but do that in a transparent way to the user. So we could do something dirty here, which is to say when the request comes through, say for any request for an Android widget text view, we actually want to return a button. which is legal from a class casting standpoint. AppCompat actually does something similar at the layout inflator standpoint to give you its own AppCompat versions of widgets. But if we try to do this, actually, the framework has your back here, where it's not very readable, but this is a link to something deep in the ART runtime that basically will, if you try to do this, it's going to basically barf and drop the application and say, hey, like, I was trying to load this class, and it gave me back something else entirely, and I don't trust it now, and so I guess we're going to crash. And so that's good, I guess, from a security standpoint. You're not going to get sort of weird, unexpected behavior. We can try also maybe getting around that with a result swapper, which is to say, whenever we get a text view, go ahead and proceed with that, but then go and do a separate lookup of the button class on our own and try to return that. And then you'll get the same error here because it's checking just the result at the end. So that's good. But what if we want to try to take this a step further and really try to circumvent it? So has anyone here worked with proxies in Java before? All right, 3 people. So proxies in Java are basically, if you've ever used retrofit, this is how it works under the hood, where you can basically give it an interface and then it creates a new sort of anonymous instance and you can control method invocations on it. So say we want to have a proxy class here. I realize my docs here are giving away how this ends. So say we want to, every time we get a list, we want to return some other class for the list. That'd be a really potentially terrible thing to do, but hey, like you get a list and you decide you want to make them all immutable, so we decided to do this in a terrible way. So we can create a new proxy instance, and we can try to basically just return this fake class. This one also actually fails sometime in the ART runtime, but I couldn't actually find anywhere that it correlates to, and it seems like it fails mostly by coincidence, not necessarily that it expects it. It tries to cast it to a class, and that just fails with the class cast exception, but it's not like a specific error message saying, hey, you were trying to do this, and now it's this. So that's an example of something like bad that you can try to do, but the framework's going to stop you. Now I want to talk about two more potential use cases. So we can package in, so in Google Play Store, you can't dynamically download DEX files on the fly. It's against the policy. Facebook tried to do it, and they were told no, and then they changed the policy the next day. But you can actually ship your own DEX files in the app, and you can load those because you're not loading them remotely, and that's the only real sort of issue with it. So if we go through and say we have a, say we want to package a DEX file in assets. So I've got this, there we go. So I've got this interface called say hello. How do I, there we go. Which is a simple interface, just you call say hello, that's really small. Say hello, and it returns a string. And we want to package in different implementations of this as a DEX file. So we can do one here in assets, which if we go into assets activity, basically we want to go into this assets helper class defined here, and say that we want to get a class loader that's pointing to our assets directory, and then load a DEX file out of there. And so this is just a helper method. I've got this byte buffer utils class that you don't really need to know too much about how it works, but basically you point it to a file that's a DEX file, and it loads it up into a byte buffer. So you can do that. You can then get a class loader out of that with the standard creating a new path class loader, and then we can actually just tell it, hey, go and load up this hello impl class. And whenever we do that, we can actually just run in here, go into assets. We'll get to this dialog later. And we'll see, hey, it loaded this string from assets. And it's just telling us that we've loaded this now sort of remotely, not from our class loader, but not from a DEX file we've downloaded on the web either. It's just a different file that we packaged in assets. We can actually do the same with resources. So this is a DEX file that's just packaged directly into res raw, which I guess if you do it in resources, you could do some fun things with like resource qualifiers and splits. So if you want to have like a night version of your DEX file, you could do that. Feasibly possible. So that's a potentially like good use case of this, and there are some like public SDKs out there for doing this kind of stuff. This is also potentially useful for being able to kind of cut down on like what is actually showing up in your installed binary if it's not all the features that a user has to use. So the last thing that I want to get into, and I'm rushing a little bit here because I'm taking up more time than I thought. I want to show this neighbor app. So this is where you get into the really morally ambiguous stuff. So this is an app. It's called Neighbor. If we go and look at the source code for it, it has a main activity. Yeah, it's fairly simple. It has this say hello method, says hello neighbor, and it's got an API as well, just a retrofit API where you can post an image or get some private info or create a user, things like that. So this looks pretty innocuous. I've built the app. I'm running it in my code here, or running it in my emulator. And but remember, all we need to do is just point to installation location of APK, which means that if you query for package info for other apps, like when you're doing intent resolution, you actually get that application info back, and you can read their source directories, which means you can actually just create a path class loader pointing to their directory and start loading their classes with no extra permissions required. So that gets fun. So if we go through and run through here, so we've got a few examples in here. So here's a very trivial one that just say hello, which actually goes through and looks up that say hello method that we found here. I'm hard coding it in this case because I know where it is, but whenever we go through here, we can actually say create a spy and say that we know that we want to get this main activity method in our neighbor app and this declared say hello method, invoke it, get the string back, and now it's giving back the string that we have here. If we want to take this a step further, we can actually go through and potentially do some bad things here. So say we want to go find their build config class and print out all the static final fields in it. And that actually suddenly becomes trivially easy because all you have to do is iterate through the ClassLoaders classes and find one that ends in build config. You can make it a bit more intelligent if you want, especially if they're doing obfuscation, but it's sort of trivially easy. And because these are statically defined final constants, you can actually print out what their values are right here. The next thing, so remember that API service that we looked at? So we can actually go through here, look that up, and we can do the same sort of like printout of everything that we see in that service. So now I'm actually reading this other app's private API that actually talks to their network and backend. And because I actually went through and hard-coded it in there, I can actually go through, and if you've ever used retrofit before, you'll know that all you have to do is give it a class, and then you get a full retrofit working instance. And because I had, say, API keys and whatnot hard-coded into that, I can actually go through and start running their network stack in my app. And I don't think my internet's actually connected, and I don't think it's going to work. But yeah, anyways, this is uploading an image to Imager somewhere, but I'm running another app's code in my app. Again, with no extra permissions or anything required. So does anyone here do this in their apps? Who here uses Play Services? Congratulations, you all do this in your apps. This is how a lot of Play Services works, where basically it just reads and runs code out of the main Play Services app in your app. Yeah, okay, so that eventually failed. Now you might be thinking, like, this seems like someone can make an app that could actually go through and basically, like, if they ship a decompiler in the app, it could go through and start just decompiling other apps' code. And you'll be happy to know that someone's already built this. It's on the Play Store. It's this app called Show Java. And you start it up, and it just freezes the emulator, apparently. I was so close to the end of this without... Oh, there we go. Yeah, so say we pick this. So you can look at all your installed apps. Say we pick this, pick a decompiler, runs through. You'll start seeing a whole bunch of class names that it's decompiling here. And there we go. An error occurred. But we've actually got classes in here. And there's a source code that it decompiled out of this other app just by looking at its, I guess, globally readable installation directory. And yeah, so that's it for my demo on here. I'm rushing through here a bit for time reasons. I do want to get back to the final part of this presentation, which it's called Show Java. There we go. So yeah, so some final closing notes on this. So this does get harder in Android Pie, specifically with the new private APIs. This is all through a new initiative, not confusingly called AppCompat, which is different than the other AppCompat. So things like the Black Mirror setup, where we were replacing and hijacking the ClassLoader at runtime, that doesn't work anymore in Android Pie once you start targeting SDK 28. But all the path ClassLoader stuff still does. And second is to just basically be mindful of this stuff. So like I said, this is not something that I recommend anyone in here go and do. We prototyped this just on debug apps to try to get a better understanding of how class loading works, but it's nothing that we would ever feel comfortable shipping in production. Yeah, and it's something to keep in mind also from the standpoint of any app can go through and read your source code. If you go and ask a security person, they're going to say, well, yeah, once you ship it into production, you don't have any control over it. Someone could download the APK and start running around with it. So that's where tools like ProGuard and whatnot come in. But the fact that you can also do this at runtime is added consideration for it, especially since we're all presumably running, our internal unobfuscated debug builds on our phones alongside all these other apps that can actually go through and read it just fine. Security is hard, but we can also make it not trivially easy for people that want to look at it. And I hope that maybe this demystified a little bit of how class loading works on Android and just how much you can actually do with it. Because at the end of the day, it's not magic, it's just code. And that's it. Thank you.